A very good morning to all of you. I will be starting the session by 11:20. Okay, please wait for 2 minutes. Just wait for 1 minute. I will be starting the session of COA Gate class by 11:20, and just wait for 1 minute. Okay. Okay, so a very good morning to all of you. Hope all of you are fine. So in the last class we have started with the gate class regarding the COA, and I discussed the syllabus of the gate more or less. So what are the strategy also that you need to follow to get a good score in gate examination, that also I told you. Okay, and I have discussed the instruction set in the last week, and I have discussed some of the problems. Okay, and last class I discussed one problem, only the problem statement I have given, but I have not given the solution of this. So let's solve this problem in the classroom, so we can do it the addressing mode after the solution of this one. Okay, so let's have the board work. Okay, so many of you may have solved this one. I know Preyoshi, she has solved and gave me the answer. Still, as I have given the problem, so I like to solve this one first, then I will go for the addressing mode part. Okay, now this is the GATE 2018 question based on the instruction set, and you can see from the question that it is written here, a processor has 16 registers, so it is starting from 0 to 15, and it is having 64 floating point registers. I will be telling this one slowly because this type of question you have to read carefully. Okay, because the length is huge, so you have to be very meticulous while you are reading the questions. Okay, be careful. So 64 floating point registers starting from this 0 to 63, and each of the instruction is having 2 byte. It is given already, it is 2 byte instruction. So there are 4 categories of instruction given: type 1, type 2, type 3 and type 4. Okay, now each type it is given some specification. So it is having type 1 category consists of 4 instruction, each with 3 integer register operand. Type 2 it is having 8 instruction, okay, and 2 floating point register operand. 3 type is the 14 instruction, and each with having the one integer register operand and one floating point register operand, and a fourth type of instruction. They have not told that how many number of instructions are there. N number of instruction they have told, and each with one floating point register operand. Okay, so let's solve this with this type of problem, and you can see the different question banks are there, right? So you can go through the practice paper and you can check. See, this pattern is common. This pattern, the pattern I am telling you now, this pattern, like 3-4 years consecutively this type of question they used to give, but a little bit of deviation is there. Okay, now you can see this one. When you are going for this part, like you have this 16 integer register, right? 16 integer register means what? So I told you in the last class, when you have a stack of 16 registers, so what is going to happen? You have 1 2 like this way. Okay, 1 2 3 like this way. You have 16 number of registers. Okay, and so each of the address, so 16 we can write, 16 should be written as 2 to the power 4. Okay, so each, if you see the address field, so each of the address field will contain 4 bits, because this n is basically 4 here. Okay, so this is the thing. Now this is for which case? This is the normal integer register. For integer register, this is the case. Okay, now when I will come to the floating point register, the size is a bit higher, so it will be starting from, suppose, 1 to 64, okay, or 0 to 63, same thing. So you know what is the number of bit that is used for the address field? 64 means you have 2 to the power, how much is 64? So that value number of thing you have to do it for the, so it is 2 4 8 16 32 and 64, so it is 2 to the power 6. So 6 bits we will be having for the address field of this. Which type of register? This is the floating point registers. Okay, now the thing is that you have 4 types of instruction. Now see one by one. So when you have 4 types of instruction, we will be just writing one by one. I will be having the 4 types of instruction. Okay, so when you are having 4 types of instruction, so I will be writing the type 1 instruction. Type 1 instruction, it is given that there will be 3 registers, like the instruction register. So opcode is mandatory for things, so opcode is mandatory, and you have 3 registers. If you see the question here, you can see type 1 is having the 3 integer register. Okay, so 3 integer register for type 1. So I am drawing it accordingly. So you have 3 integer register means you have, suppose, register 1, register 2 and register 3. You have 3 integer register, and you know what, how many number of bits are there to represent the address of integer register? 4 bits. Okay, so this means 4 bits address are basically required. From there you have found, right, the how many bits are required, because each of the register address is 4 bit. From this, because you have 16 number of registers available, so 4 bits are there. Now what is the length of the instruction? The length of the instruction is given. Length of instruction in the question, it is given as 2 byte, right? So when you are talking about the length, it is 2 byte. 2 byte means is basically 16 bits. Okay, 16 bits. So you have the 16 bits here, right? So you have 16 bits. Now easily you can find out what is the bit required to represent the address of the opcode part. Okay, so definitely if you just, this is a 4 plus 4 plus 4 is basically 12, and definitely 16 minus 4 plus 4 plus 4 will give you the number that is 4 bits are required to represent the opcode. So this basically from here we can say we are writing it 4 bits. From this equation we will get. So for other types you can do it parallelly. For other types of instructions also we can find it out. Like if I go just type 2 instruction, you can check the type 2 instruction has 8 instruction, 2 floating point registers are required. So I have to draw it for type 2 also. So when I am going for type 2, so for type 2 what I can write, so for type 2 we can write it here, another type of instruction which contains 2 floating point. As you have seen, 2 floating point registers are there, suppose 1 and floating point register 2, and you have the opcode, that is common part. Okay, so floating point register means, you have seen floating point register means how many number of bits are required. It is 6 bits are required to represent the address. Okay, so for this case you can find that this floating point register also required the 6 bits, and here also you require the 6 bits, right? And here also the total length of this 2 byte, that is 16 bits, right? So how many number of bits are required for this opcode? You can easily subtract this 16 minus 6 plus 6, you will get this 4 bits. Okay, so for type 2 you have the 4 bit for the opcode. Okay, now come to the type 3, because it's a lengthy question. Type 3 category consists of 14 instruction, each with 2 register operand and 1 floating point operand. Sorry, say 1 register operand and 1 floating point operand. Okay, so one thing you would see, when you are having this one, I will just go for the type 3. So when you have the type 3 expression, so when you have the type 3 will be having the same structure of opcode and all these things. So you have this opcode and you have one instruction register, another you have the floating point register from the question itself. Okay, it's better to take the snapshot of the question. So when you have this one, you have this 6 bit. What is the instruction? This is 4 bit, and this is the floating point is 6 bit. So how many? So it will be 16 minus of 10. So that will give you basically 6 bit, right? And the last type is type 4. The type 4 will give you another type of opcode. Here what is happening here, you can see there will be, so the question is a bit lengthy. So you have the type 4 category, the n number of instruction, each is a single floating point register operand is there. Okay, so when you have this type of instruction, each of this is only having 1 floating point. So you have only 1 floating point register here, and you know this is 6 bit. So this opcode you have to check, this opcode portion will be 16 minus 6, that is 10 bits, right? So this is the thing that we have jotted down. Now how many instructions are there for each of the cases? You can check. For type 1 you have how many instruction? You have 4 instruction. Type 2 you have 8 instruction. Type 3 you have 14 instruction, and type 4 you have n instruction. So I will be writing here just for sake of remembering. Okay, so type 1 you have 4 instruction like this. Type 2 you have 8 instruction like this. Type 3 you have 14 instruction like this. And type 4, the question is type 4 in instruction, in value you need to calculate n number of instructions are there. Okay, so when you are having this many number of instructions are there, so what you are having this one, so we can find that if you have 16 bits, how many possible, because each of the instruction having number of bit is 1 to 16, so how many number of possible combination, there will be 2 to the power 16 number of possible combination of the instruction. So you have 2 to the power 16 number of possible combination. Okay, now if you see, maybe this question a bit you feel a bit tougher for this. So for the first type you have 4 number of instructions, for first type 4 number of instruction, and for each of the instruction you have the for each of the instruction you have the 4 possible ways, that is 2 to the power 4 possible ways. For each of that you have 2 to the power 4 possible ways, and for each of that you have another 2 to the power 4 possible ways. So for the total thing, if you see how many number of, for each instruction how many possible combination of bits, 2 to the power 4. For each of the possible combination of bit, how many possible combination of bit for R2, it will be again 2 to the power 4, and for each of that you have another 2 to the power 4. Okay, so if I just calculate this one, 4 number of instruction, for each of the instruction R1 value is taking 2 to the power 4, for each of the R1 value the R2 value is 2 to the power 4, and for each of that it will take 2 to the power 4. That is 3 instruction register, right? And then if you go for the type 2 instruction, just check the type 2 instruction. Type 2 instruction is how many? 8 instructions are there. Each of the instruction will contain how many possible combinations? 6 bit means 2 to the power 6, and for each of the combination here how many possible combination? 2 to the power 6. So 8 into 2 to the power 6 into 2 to the power 6 will be the possible combination of the second type. So if I write it here, so 8 number of instruction, for each of the instruction you have 2 to the power 6 into you have 2 to the power 6. 2 FR possible combination. First FR1, second FR2. Now for the third one, third type, you can see here there are 14 number of instruction for the third type, and one instruction register having 4 bit, that is how many possible combination for this? 2 to the power 4, and for each of the case you have 2 to the power 4 number of combination. Okay, so you can write down here plus 14 into 2 to the power 6, okay, sorry, 2 to the power 4, because you have this 4 bit. For that also you have each of the instruction register having 6 bits, so for each of the case you will be having 2 to the power 6 number of combination. Okay, so plus n into you have the last number, that is 2 to the power 6. Okay, so from there you have to calculate the value of n. That is the way of solving this type of question. Maybe it is feeling you feel boring like this, but there is no other provision of solving this one. You have to be a bit patient in this type of and you have to just go through step by step. So you can calculate the value of n like this way. Okay, okay, now let's come to, that is the previous class, the question I have given, this is a probable solution, and if you calculate the n value you will get the 32. Okay, now today we will be starting about the addressing mode. Okay, now you can see here in case of 8085 or whatever 8086, different types of processors you will be dealing with, and there are different types of registers and memories are there, and you have to fetch the operands. Like the operands, you have some instruction, the instructions are stored in the memory, so you know how to fetch the instruction, decode the instruction. In the pipeline architecture you have seen all these things. So So the way you are fetching the operands, whether from the register end or the memory side, that will give you the addressing mode. Okay, now in the addressing mode you can see there are different types of addressing modes that are present here. So for that we need to go through the addressing mode part. So what is given here, the operands can be placed either in the register or the memory, and you have to fetch the operand and you have to do all these things to execute the instruction. Okay, now the way you are just fetching the operands, that is going to be whether it is simple direct addressing, indirect, or register direct, register indirect based. Lots of the like 9 to 10 addressing modes are there. How you are fetching the operands, that you will get from this addressing mode. Okay, so I will be briefly discussing about the theory of the addressing mode, then I will be coming to the application or the question part. Okay, now let's come with the immediate addressing mode. Now in case of immediate addressing mode, what we can find, that the operand value is specified in the instruction. Okay, you know this one very well. Some books it is written in case of capital H, that is the hex value. So when you are moving the thing, that is if I just draw a simple thing, you know this one earlier, but for sake of, so you have the accumulator here and you have the value 15 here. So what you are going to do, you want to move this value to this accumulator. So in the instruction itself the operand is specified. So this is the operand which is specified in the instruction itself. Okay, so this is the normal immediate addressing mode. Okay, this is a move immediate or add immediate, when you are adding something with the accumulator. So whatever is the value, that will be added with the content of the accumulator, and the resultant is basically stored in the accumulator itself. Maybe the last part was boring, because numerical of gate is always a boring part still, but we have to solve some of the numericals because this is not the normal class. So you have to be a bit problem analysis oriented, your mindset have to be, and you have to understand the type of problem that may come and that the approach of solving this. It's not like solving the problem, what is the approach that you will prefer to solve the problem. You can see the question paper and you can easily understand the approaches more or less similar. It's not like that আমি পারবো না গেটে এরকম নয়, কিন্তু ঠিক আছে চেষ্টা করলে সব হয়. So you have to be a bit strategic. Anyways, so you can see this is the add immediate. So you have some accumulator value. Okay, suppose it is something 5 is there, 05 is hex is there, you have some register which contains the 3e value. Okay, so you are adding these two things and you are, whatever is the resultant, that you are again putting in A. That is the add immediate, ADI. Okay, now what is the register addressing mode? In case of register addressing mode, the operand is specified is one of the processor registers. That means here you see the 15H is not written explicitly. Okay, but here it is written A or here it is written B. That means whatever is the content of A is the accumulator that may be containing some value, and you are moving the content of A to the register C. Okay, that means it is the destination part and this is the source part, right? So this is the destination, this is the source part. So this is simple move and this is the register addressing mode, right? Now when you have this add B means what? Whatever is the content of A, whatever is the content of B, that will be added and the resultant will be stored in the accumulator back. Okay, so this is the simple register addressing. Why it is at simple register addressing? Because the operands, this is very important, the operand is specified in one of the processor register. এখানে কোনটাই হয়েছে, it is A or B. This A and B are working as the processor register. Okay. Now come to the register indirect mode. I will be giving you some problem, then your if you have some doubt, the doubt will be cleared. Okay. So register indirect addressing mode, you can say the register, suppose I am telling you move A comma M. Okay, so A comma M, the address of where the operand is, you have some operand here, right? But suppose R1 is containing a location of 8 value of suppose 8012. So previously in case of register direct mode, the value of 8012 will come to A. But in this case what will happen, 8012 will actually point one location in the memory. Okay, the location of 8012 will point, that is the location of memory will be 8012, and whatever suppose it is 65 is there. Okay, so this value will come to this A. Okay, the register indirect means register content will have the memory address, and that memory address is the basically the effective address that will contain the operand value, and that operand value will be moved to the accumulator A, not the direct 8012 will come to. Okay, in case of register direct 80 example jodi agertai hoto ki hoto 8012 will be there in this case. The same example if I have given here, that C is another register, the previous example. So C is another register here, that is, or A is another register here that is containing 8012, and C, that means C will be having this 8012 directly for register direct, but for register indirect this will point one address in the memory, that address will contain some operand, and that operand will be have to be fetched to accumulator. Okay, let's have some example here. You can see that this is, I am talking about some HL register. You know the HL register pair will contain the address of the instruction, next instruction. Okay, so you see now the present instruction is containing 2805. Okay, now whatever is the value present here is 2805 is A9. Okay, now if it is register indirect, 2805 will contain, this register pair is address is 2805. This 2805 means the address location you have to find out 2805. Then whatever is the content in the address location, that is going to come here in the accumulator. Okay, so this is the way actually we do the register indirect. This is another example. It is not, I have not given direct register address, I have given the memory address, but this memory address is pointing one location, that is HL pair if you consider, and that address is containing the operand. Okay, now direct addressing mode we can find that the direct, here STM in load accumulator or store accumulator. Okay, so in this case you can see whatever is the content of this address 2805, that content will be stored in the accumulator in case of LDA 2805. Okay, in case of LDA 2805, and in case of STA 2803, so whatever it stored, that is the stored the accumulator. Okay, so it stores the data from the A to the location specified in the instruction. That is the thing. So let's have some example here. Now in this case, you know this one still a bit of brush up. So if before execution you have this one. Okay, now this 2805 is the containing 5C. The location 2805 is containing 5C. Load accumulator, whatever is the content of 2805, that will be given to accumulator. So you are loading the accumulator with the content of 2805. Okay. Now the STA 2803, what will happen? So previously the accumulator was containing 9B. Okay. Now you are storing the value, okay, to the location 2803. Okay. Previously 2803 was blank. Okay. Now you are storing the content of this accumulator to the location of 2803. Okay. This is the STA 2803 hex. Right. So this is all about the direct addressing, LDA and STA. Now come to the indirect addressing. Now what is happening in case of indirect addressing? Indirect addressing, the address, or you can say the effective address of the operand is, I will just go to the example part. It will be easier for you, right? Now before you can see indirect addressing, you can see that A will be having, so something will come to A. What is going to come to A? Whatever is the content of 2802, will it come to A? No. 2802 will contain another, you see the 2802 is actually this location, okay. So this location is basically containing the two successive, because it's a 1 byte, right. So the two successive location is containing the address, another address, that is 2806. So whatever is the content of 2806, that should come to the accumulator. Is it clear to you? So the direct addressing is the whatever is the content of the address, that will come to the accumulator, whereas in case of indirect addressing, whatever is the content of the address, that is another address that holds the operand. Okay. So here 2802 is holding the address of 2806 and 2806 is basically holding the value of FF. So this FF is ultimately coming to the accumulator. Okay. So this is the way we are actually having the indirect addressing mode. Okay. Now come to the implied addressing. In case of implied addressing, the operand is not explicitly told. Like R1, R2, we are not explicitly telling the name of the operand. Okay. So the operand is implied. This is very implied. That's why the naming convention is implied. The operation is implied by the instruction, like CMA, complement accumulator, or complement the carry flag, or the set carry flag. So these are the instructions we are using for the implied addressing mode. We are not using R1, R2, anything we are not using. From the instruction it is implied that where the operand is situated. Okay. So the operand is hidden or fixed in the instruction. Now the problematic situation arises, the relative addressing mode. Okay. Now in case of actually the relative addressing mode, you know there are different types of addressing mode. You have the relative addressing mode. Just one second. Okay. So anyways, so what I was talking about, the relative addressing mode. So relative addressing mode is a type of relative addressing or index addressing or increment, decrement. So we are not actually using with a single address. We have some address value and we are also having some content, okay, some register value, whether it is a program counter or index register, whatever, those things are incorporated in this concept. Okay. So in case of this relative addressing mode, whatever is the content of the program counter, that is to be added with the address part of the instruction to obtain the effective address EA, right? So this offset part is can be positive or negative, that is very important. So in GET question we have seen we will be using one problem with a negative offset. Okay, so these things will be there. Now when we will be having this relative addressing mode, this offset value is added with the program counter to effectively get the actual location of the operand in the memory. This is the way we are actually calculating the relative addressing mode, the final or the effective address. I think you have done some of the examples in the normal COA class also. Okay, now let's have some example here. You can see in this case the offset value is 04 and the program counter is containing a value of 2800. Okay, now when the program counter is containing the value of 2800, it basically shows this value, this location, right? This is the thing, and generally one instruction is like a 2-byte instructions we are taking. So this 2 is added with the program counter, that is this instruction is completed and you are going for the 4 offset, so offset part. So ultimately the location will be this one, so operand will be this one. Okay, so this is the way we are actually calculating this one. Ke phone korche eto bar dhore? Okay, so the thing is that this relative addressing mode is also known as the PC relative addressing mode. Okay, and we have told you the instruction specifies the address of the operand as the relative position of the current instruction of the address. Okay, like you have some example you have done in the TK Ghosh, like you have the jump instruction, like jumps JR20 you have used, like jump instructions you are using in the 8051 microcontroller. Okay, to get the effective value of this operand. Okay, so if you are using like JR20, you have you know maybe the whatever is the PC content, the JR20 will have, like I am just telling you the example you have already studied. So JR20 you have just studied in previous class, so you know this one. This is a 2-byte instruction you have seen, and this 2-byte instruction means whatever is the PC, that is a program counter value, that will be added with 2-byte, and then the value of offset that is given in the instruction will be added. Okay, so this is the way we actually calculate the relative addressing mode. Now come to the index addressing mode. In case of index addressing mode, the index register content will be added with the instruction part given in the, that is the address part given in the instruction. Okay, so every time we are adding the address part of the instruction, previous case we have added with the content of PC, now we will be adding this part with the content of the index register. Okay, this is the way we will be adding the content of the index register with the content of the or the address part to calculate the effective address. Another important thing is that this we always use as positive. Okay, and the index value changes, but the base remains same. Let's see the next example. So in this case we have considered the base value is supposed to 2800 for all the cases. Okay, now the effective address of the operand, I know the base value, the content of the base and the content of the register needs to be added. Okay, so what is the thing? So the base value is 2800 and this is the thing, right? So you have to add it, here it is 0000, so you have to add this to, so it is the effective is this one. So 2800 will be added with, now IX value is 0001, right? So 2800 will be added with 0001. So you will be getting the effective address as 2801, that is this value. So this operand will be fetched. Okay, so 2800, the ix value, that is index value, is 0002. So it will be added, you will be obtaining 2802. So 2802 means this value will be fetched, right? So this is the way. So what you can find, the point I mentioned you, the base value is fixed, the base value is not changing, but the index values previously is 0000, then 0001, then 0002, 0003. This is the way this is going to be changed. Okay, this is changing, but this base value is not changing, this is fixed. Okay, now next is base register. So we can call it normally base value. So here base, the reverse thing will happen, the base value is going to be changed, but the offset value is not going to be changed. The same type of concept. Okay, so let's come to the example. Previous case what we have checked, that 2800 was fixed, right? So the base register content plus the offset we will be using this time, and the base value is not fixed here. Previously base value was fixed, right? But here the base value is not fixed, base value is changing, but the thing is that this offset part is fixed. You can say everywhere it is 0001, 0001 every. So this 2800 part is changing, sometime it is 2801, this 2802, this is happening. So base value is going to change here, but the offset is going to be fixed for this case. This is the base register. Okay, and mainly this mode is used for the, this is very important part, that is for program relocation. This is very important. Program, you have the program relocation part, that is used. There we will be using this base register addressing mode. Okay, now the last one is the auto increment and auto decrement. The question used to come from base register, auto increment. These are the critical is the thing, the gate, the paper setters interest is more, right? যেখানেই কঠিন হবে পেপার সেটারে সেখানেই গেটের জন্য কোয়েশ্চেন দেবে, নর্মাল কোয়েশ্চেন হ্যাঁ ঠিক আছে মানে fine, but in case of gate we will prefer the areas where the problem will arise or the conceptual thinking must be cleared in those sections, then only you will be capable of answering all these things. Okay, so in case of auto increment, the thing is that the register value may be the HL pair. I have given one question, in that case HL pair is considered. So the register content will be incremented or decremented before or after its value is used. Okay, so this is the case in case of auto increment and auto decrement addressing mode. Now let's see the example. Okay, so in case of, suppose it is auto increment mode of operation, so every time the value is fetched, the HL pair value is incremented. Okay, so it is fetching first time the HL pair value was previously 2802, now it has been changed to 2803, now it has been changed to 2804. So the HL pair is incremented after the value is used. Suppose it is fetching this value, then it is incremented to 2802, then the value of 2802 is fetched, then it is auto incremented to 2803. But in case of auto decrement, it will just decrement, then it will fetch. The concept is a bit different. In case of auto decrement, is a slight bit of difference is there. Okay, now this type of problem you have seen previously, but we will be having this type of problem to just for sake of another practice problem. Okay, so we can check this one. This is the question given. you have to calculate the effective address of the operand for all the addressing modes. Okay, so the question will remain as it is. See, this 2000 and 2001, the instruction is stored in these two locations only. Okay, so this two location 2000 and 2001, you have some instruction and some operand. Sometime it will be working as the operand, sometime it will be working as the address to the next operand. This is the thing. Now for this immediate addressing mode, what is happening, the value, some opcode is there and some operand is there, right? So opcode value, suppose we are writing MVI, suppose we write some content 15H, the way I told you. Here instead of 15 it is stored 500. Okay, some value is stored here in the next location. So what is going to happen, if you are using immediate addressing mode, the content of 500 is going to come to the accumulator. Very simple example. Okay, very easy. So if you have some opcode and you have some operand will be there in the next address. Suppose this is a 200, next you have the 201. Okay, so the address are like this, and whatever is the content here, that will be fetched to the accumulator if it is the immediate addressing mode. Now in case of this the second one, that is register addressing mode, we will have the register R1 which will contain the value of the operand. Okay, so whatever is the content, like I have told you, like one example, move A comma R1, suppose may be the example. So whatever is the content of R1, that is going to be fetched to the operand. So the content of R1 was 400, that is fetched to the accumulator. So this is the simple register addressing mode. Now come to the register indirect addressing mode. So in register addressing mode, the content of the operand was fetched to the accumulator. But in register indirect, this R1 actually storing the address. So if it is R1 containing 400, this 400 is not going to come to accumulator. So what it is going to come, or what it is going to take, the 400 is going to point a memory location 400, and you have to check 400 is going to point a memory location 400, and whatever is the content within the memory location 400, that is going to come to the accumulator. Okay, so this is the register indirect addressing mode example. Now come to the direct addressing mode. In the direct addressing mode, we know the address of the operand is written in the instruction. Okay, so if you see the instruction, one address is already there, that is 500. Okay, so these two things will contain the instruction. So this instruction part, in the address part, it is already 500 is there. The value 500 will be considered as the address. Okay, so whatever is the address, content of the 500 address, what is the address containing? This 500 address is containing 800 value. Okay, so 800 value will come to the accumulator. Okay, so this 500 is basically acting as the address. This address means this 500, and this 500 is basically contains the operand 800. So this 800 will come to the operand accumulator. Okay, so this is the way we are actually fetching the things. Okay, now come to the next one, indirect addressing. So the 500, what I told in case of indirect addressing, the 500 value, address value, is not actually keeping the operand. the 500 address value is keeping another address value 800, that is actually keeping the operand. So 500 address value is keeping the 800 address value. So come to the 800 value. So within 800 which value is stored? 300. So ultimately operand is what? The operand is 300 and it will go to the accumulator. Okay. Next one. So if you go for the relative addressing mode, so or it is also known as the PC relative addressing mode, right? So the PC content will be added with the offset value. Now you can see that PC content is 200 here and the offset value is given in the instruction itself. Okay, so this PC will be added because the instruction is supposed to be 2 bytes. So 2 byte will be added with the PC and then it will be added with the offset to calculate the effective address. So you will get the effective address as 702 because the 200 will be, this 200 will be added with the 500 and as this instruction is 2 byte, so we will, the extra 2 will be added. So you will be getting the effective address as 702. Okay, and the content of 702 is basically 325, that is going to come to here, right? So this is the way we are actually calculating the PC relative addressing mode. Now let's come to the index addressing mode. In case of index addressing or base register, whatever, the value of base is to be added with the index register. So value of the base is basically is considered to be this part and this XR is the base register, that the index register is containing 100 here, right? So here you can see this 100 is basically the value of the index register and the base part is containing the 500. Okay, so if you get this value, add this 2 and you will be getting the 600 as the address of the or effective address. So 600 means this location and this location contains the operand 900 and this 900 is going to come to the accumulator. Okay, so this is the way you can calculate the effective address and the operand value if some question is given. Now next is 2 examples are remaining, Autoincrement and Autodecrement. In case of Autoincrement, what is happening here, please just listen minutely. 2 things are a bit different. In case of Autoincrement, whatever is the, here HL is not given, only R1 register is given. Okay, so the value the value of R1, that is the containing value 400 is going to represent one address that is containing the 700 value. Okay, so this value is going to come accumulator, that's fine. But after that, Autoincrement means the value of R1, now it is not going to be 400. After the execution of the program, the value is going to be 401. Okay, so after the execution or fetching of the operand, the value of the register will be incremented automatically. Okay, so we will be having 401 after the execution of the Autoincrement instruction. Okay, now in case of Autodecrement, please see this one carefully because they used to ask the question from this section, because you can see the accumulator value will be what? The register value is same 400. Okay, so the 400 content is 700, but you see that this is not coming here. Okay, so what it is coming, initially it is decremented first, and then what after the decrement value, whatever is the value, that is coming to the accumulator. So in case of auto increment, you fetch the value, then increment the register, and for auto decrement, you first decrement the value of the content of register, then whatever the address it is going to point. For this case, the initial value was 400, then it is decremented to 399. Now this is going to be the effective address, so the content of this is 450, that value is going to be fetched in the accumulator. So this is the example of auto decrement addressing mode. Okay. Now this is the example, this is for your assignment part. This is one example. You know, RISC machine is the reduced instruction set computer machine, and it is basically for this question. Here each instruction is exactly taking 4 bytes. Okay, and you can read the question. Conditional and unconditional branch instruction, because I told you for whether it is base index or you have the base register index or index addressing mode, all this case you have the branch type of instruction, or whether it is PC relative addressing mode. So for this case you have to do what? You have to calculate ultimately some offset value. Okay, now some instruction set of instruction is given. So let's try it once again. The conditional and unconditional branch instruction use PC relative addressing mode with offset specified in byte the target location of the branch to the target location of the branch. Okay. Further, the offset is always with respect to the address of the next instruction in the program sequence. Now the program sequence is given. Okay. Wait, ma'am, auto increment, auto decrement. No, you just see this one. In case of auto decrement mode, you decrement the address first, and then you fetch the value of the. You fetch the value to the accumulator. Ekdom. Okay, so the thing is that we can see the instruction set. So this is the sequence of instruction. So maybe today I will not able to complete it. So in next class I will try to complete this get question. Okay, so try to solve this one for your assignment part, or you can just try to solve. Next day in class also I will solve this one. So one hint I can just give you, that suppose you have this 4 instruction, like 4 instruction. So each instruction, suppose you have the 8000 is the first address that is going to be stored in the program counter, right, for instruction I. Okay, and you can say this is the first instruction. This is the first instruction. First instruction. Similarly, you have the second instruction I plus 1. So as the program, each of the instruction is taking how many number of bytes? 4 bytes. So what is the starting of the next? It will take 4 bytes, right? So the next instruction will start from 8004, right? So 8004. What will be the next to next instruction starting address? Another 4 will be added with this, so it will be 8008, right? So another one I plus 3, the last instruction, what will be the value of the program counter? Then 8012. Now you can see after this, the target of the branch instruction is I. Means after this it will just target again I. Okay, so what is going to be the next after this? What is going to be the next? The next instruction value after this, it is going to be the program counter value will be the 16, the target instruction value. Okay, address of the target instruction. Okay, so we can know the in case of this offset type value, so we have this, we can write it in this fashion. Okay, the effective address, now the what is the effective address? The 2016 is the instruction address, right? The target instruction address. This is what 8016. Okay, so the effective address is basically 8016. This is the effective address. Okay, now we know this one. Up to this I am just telling you. Okay, so this effective address value is this, or you can say the program counter value is this, because it is PC relative address. The present after doing the +4, don't get confused, do not add +4 with this. Already +4 I have added, because previous the program counter value was 208012 and now I have added 4, and now it has been, because it's a 4-byte instruction, that's why the last value was 8012. I have added 4 with this, so now it is 8016, and then you have to add some offset, then that is going to be the effective address, right? Then it is going to be the effective address. Now what is the effective address? Because the effective address is the address of I. What is the address of I? Can I write it in this fashion? So the effective address means address of I is what? I can see the 8000 is basically the effective address, because address of I is basically, because it is going to target, where it is going to target? It is going to target 8000, right? So effective address is this, and the program counter after adding 4, it is the program counter value is this, and you have the offset value. Okay, now the question is the offset, you have to calculate the offset value. So it is very easy. The offset value is basically, it will give you 8000 minus 8016, that is going to give you minus of so it is giving you minus of 16. Okay, so this is the way you can calculate the, and this question is not so old question, it's a recent question. So this type of question, they will not give simply one piece of code and they will ask you what is the effective address or what is the operand value in accumulator. So they will give you this type of descriptive type of question, and they will ask you to submit all this thing. Okay, so I will end the session today. So next week we will be starting with so this is another question you can solve. This is a 3 address instruction format is given. So each address field can be used to specify which of the following. Okay, so S3 is not feasible. S3 is not the feasible answer. Okay, so here, and here 3 cases S3 is there. So the answer is whether it can be a memory or a processor register. Okay, so I will end the session here. Thank you for attending the classes. I request you to attend all the classes so that the concept for all the subjects will be clear to you. Okay, so